Hey folks, I'm going to do a couple Ampere's law examples with you, two in particular. The first one is going to be called a toroid. Okay, now let me show you a picture of a toroid, and then we're going to try to recreate this together in our notes here. So this is what a toroid looks like. So it's a winding of wire around something that's not a conductor, or this wire won't touch, won't conduct to the core. We call this the core there. Now this particular one actually has an iron core, but then there's also it's surrounded by this black plastic here, so there's no touching of the wires. Okay, so it turns out that toroids have a very special property that's really kind of cool, and we're going to use Ampere's law to figure that out. All right, so we're going to try to recreate that donut in our notes. So here's what I would suggest you do. I always draw. So I start with just this. Okay, so that's our iron core or some other material. And then I have some wires going around it, and I'll kind of draw them like that. I'm just going to draw a few. There'd be a lot more. These are like representative wires. Okay. Okay, there you go. So there's 4 representative wires. And let's say the current is going this way through each of the wires. Okay, so that'd be like this. That last circle wasn't that great, but hopefully you get the idea. Mr. Mishar is definitely not an artist. All right, so there's our current, I. Okay, so if you need a moment to pause the video and finish copying that down. So here's what we're going to do. We're going to use Ampere's law to calculate the magnetic field inside and outside the toroid. So I'm going to start with inside the toroid. So like, let's say you're inside of there. So in this picture here, that would be like if you're inside somewhere in that plastic, or what's behind that is some iron. What's the field there? Okay. So all right, we're going to draw our Amperian loop, and we're going to make it concentric with the toroid circle. Okay. And if you think carefully, our magnetic field, if you look at, let's say we focus on this wire right there. So if you do your right-hand rule, like at the right here on the top of the wire, the current's going to the right. And so if you point your thumb to the right and you curl your fingers, when your fingers go through that loop, they go this way. So the magnetic field in here is going to circulate clockwise in this case. So that's going to be our magnetic field. All right. So how strong is that magnetic field? Well, let's use Ampere's law. So you got, for when we're inside the toroid, you've got, integral closed path of B dot ds equals mu naught times I in. Okay. So the path is B times 2 pi r. Okay, it's an easy path of the circle, right? Radius of this is r. Okay. Equals mu naught. Okay, what's I in? Okay, so again, we want to know how much current passes through the circle bounded by this red circle I made. So how much current pokes through that yellow circle that I just denoted here? So there's your yellow circle. How much current pokes through that yellow circle? Well, what you'll notice is every wire goes into that circle right there. Okay, so that's where each of those wires pokes into and through that circle. So basically, the current that pokes through the circle is the value of the current times the number of loops that you got. Now, by the way, that number can get really big. Like in this thing here, you're probably talking, I don't know, if I had to guess 30 or 40 loops, okay? Other toroids will have hundreds or even thousands of loops around them, okay? So that would be n, the number of loops. And that's pretty much your equation. You get B by itself, and you get the answer, mu naught I times n over 2 pi r. So notice this is basically stronger than the magnetic field made by a single wire by a factor of n, okay? So you get a nice strong field in there. Now, what if we're somewhere else? What if we are out here somewhere? What's the magnetic field outside that toroid? So I'll draw my Gaussian, or my Amperian loop. Okay. And what is I in for that Amperian loop? Okay, well, for every current that comes out of that loop there, it dives back into the loop here. So what's the net current passing through that area? Well, it's 0. So that means the B out there is 0, meaning there's literally 0 magnetic field out here. So that's a wonderful property of toroids. If I put some current through this, you're going to get a really strong magnetic field in the toroid. Anywhere here or anywhere here, you're going to get exactly a 0 magnetic field. So toroids are really useful devices for generating a strong magnetic field and keeping it controlled in a place. Okay. Now, I do have one more example on this one, and this will be quick. What if you have a sheet of current? So let's say you have a strip of aluminum foil, and you have current running through it. So let's say it looks like, here's your strip of aluminum foil, and your current looks like this, running uniformly throughout the foil. Okay, what is the magnetic field around the foil? Okay, well, if you use your right-hand rule where your thumb is the current and your fingers wrap around the foil, you're going to go in a loop, but it turns out that the magnetic field is going to kind of follow a rectangular path. So here is the rectangular path, okay, that the magnetic field is going to follow, okay? And the magnetic field in this case would go this way, and then it would go that way on the other side. So that would be our magnetic field. And we're going to give this dimensions an L and a W. So length times width is a rectangle. And if I write out Ampere's law, you get B dot ds equals mu naught times I in. Okay. Well, how much I did I captured? Well, I captured all of it. So it's just I. All right. Now, what do I get when I do this dot product? Okay. Well, it's the perimeter of this rectangle. So it'd be 2L plus 2W. So that's going to equal mu naught I in. And if we assume that L is much, much bigger than W, in other words, if we put ourselves close to the aluminum sheet, then this tends to become B times 2L equals mu naught I in. And you have your answer. B equals mu naught times I over 2L. Okay. Now, a note on this. Okay. It's constant, right? There's no variance there, right? If L is a constant, so it's the width of your aluminum foil sheet, and I is I, and that's just it. So if you're near a sheet of moving current, the magnetic field will be constant, even if you move a little toward or a little away from the sheet. That's very similar to when we had electric fields made by a plane of charge. The field near the plane of charge was also constant. So this is a similar idea, okay? Now, one more thing I'll note on this. Sometimes instead of giving you I, they'll give you something called J, which is the current density. That is the current per length of the sheet. So maybe, let's say your current was 3 amps, and let's say the width of this thing was 50 centimeters, then your current density would be 3 divided by 0.5. That'd be 6 amps per meter, okay? So if they give you J instead of I and L, you can just rewrite this. I over L is J. So this becomes mu naught times J over 2. So that's another way to write the same answer. All right, so I hope those two examples were helpful, and thank you very much.